This is our last lesson of the unit, Inequalities in Triangles. We'll first look at inequalities in one triangle, and then we'll look at inequalities in two triangles. And the good thing about this lesson is that it's filled with things, theorems even, that are just so straightforward and so obvious and so logical that I don't think you'll have much trouble comprehending it. So we start off with a property, another property. It's the comparison property of inequality, and it says if A equals B plus C and C is greater than 0, then A has to be greater than B. See what I told you? So if A equals B plus C, then A's got to be greater than B, right? Yeah, pretty straightforward. Okay, now, do you remember the triangle oops, there's the bell. You remember the triangle exterior angle theorem? Do you remember what it said? The triangle exterior angle theorem told us that the measure of this angle 1 right here, the measure of angle 1 is equal to the measures of angles 2 plus 3. You remember that triangle exterior angle theorem? Okay, well here's a corollary, and it says the measure of the exterior angle of a triangle is greater than the measure of each of its remote interior angles. So that kind of goes back up there to that little property that we just looked at. Okay, so remember from the triangle exterior angle theorem, what I just told you is that the measure of angle 1 is the sum of the measures of 2 and 3. Therefore, I know that the measure of angle 1 is greater than the measure of angle 2, and the measure of angle 1 is greater than the measure of angle 3. So this is where I always feel like saying, well, duh. Of course, right? I told you, straightforward. Okay, and here's a theorem that says if two sides of a triangle are not congruent, okay, so in this case, let's take xz. Let's take xz. xz is not congruent to xy, so not congruent. Then the larger angle lies opposite the longer side. So which side is longer here? XZ is longer, right? XZ is greater than XY. So those two angles that aren't included between those two sides, I know the larger one, which is this one, I'm going to do it with red. This is the larger one, has to be across from the longer side. Okay, and then I know that angle Z, its measure is less than the measure of angle y because it's across from the shorter side. So shorter, longer. Once again, unlike some things we study in math, I think that makes pretty darn good sense. The longer side is going to be across from the larger angle, and the shorter side will be across from the smaller angle. I think that might actually be the converse. So there it is. So let's see an example. A town park is triangular. A landscape architect wants to place a bench at the corner of the largest angle. Which two streets form the corner with the largest angle? Well, I gotta find the longest. I gotta find, it's a triangle. I gotta basically, all I gotta do is find the longest side of my triangle. This is 105 yards, this is 120 yards, and this is 175. So I know that my largest angle in that triangle is going to be across from that longest side. So that's where my bench has to go. And which two streets form that angle? MLK Boulevard and what's the other one? Valley Road. That's all you gotta do. Find, if you want to know where the longest angle is, the longest side, look for your largest angle. All right, what's our next theorem? If two angles of a triangle are not congruent, well, this is kind of the opposite. It's not exactly the converse, but it's saying the same thing only with relation to angles instead of sides. If two angles of a triangle not congruent, like angles A and B here, then the longer side is opposite the larger angle. So since I know that the measure of A is greater than the measure of angle B, I know that BC is longer than AC. Pretty straightforward. All right, so here we go. Here's a triangle, TUV, and we are told to list the sides of the triangle in order from least to greatest. So what do I have to do? I have to find the smallest angle of the triangle. That's going to be opposite the shortest side. So, of course, I need to find the measure of angle T first. So let's see, 58 plus 62 is 120. That means this angle is 60 degrees. So that's my smallest angle. So this is going to be my shortest side, right? And then what's the middle? The middle, oh wait, I take that back. 60 is not the smallest. 58 is the smallest. So this is going to be my shortest side. 60 is in the middle. So that's going to be my medium side. And this is going to be my long side. So I like to label my triangles like that. You know, kind of like baby bear, mama bear, papa bear. Okay, and so I'm listing them in order from least to greatest. So the least is TB, and it's shorter than the middle one, which is UV, and it's shorter than the longest one, which is UT. That's all you got to do. Okay, and then we have a triangle inequality theorem that says the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So what I know is that xy plus yz, xy plus yz has to be greater than the length of this third side, and so it goes for all three of the sides. So let's do this. Let's look at some examples here. Coming up are the types of problems you'll see related to the triangle inequality theorem. Can a triangle have sides with the given lengths? Well, let's see. Is 3 plus 7 greater than 8? Yes. Is 3 plus 8 greater than 7? Yes. Is 8 plus 7 greater than 3? Yes. So yes, a triangle can have these side lengths by the, what was the name of it? Triangle inequality theorem. Triangle inequality theorem. Okay, how about this one? 5 plus 10 is not greater than 15, so I can stop right there. No, because any two sides, in this triangle, you got two sides, the sum of whose lengths is not greater than the other side, so you could not make a triangle with those side lengths, okay? If any two of the sides don't add up to be greater than one of the other sides, you cannot make a triangle with those side lengths. Okay, how about this? A triangular sandbox has two sides of length 5 and 8. So 5 feet, 8 feet. There's what I'm trying to find. What is the range of possible lengths for the third side? Well, let's see. Let's start. I know that 5 plus x has to be greater than 8, right? 5 plus x by the triangle inequality theorem. Therefore, x has to be greater than 3. Okay, what else? I know that 5 plus 8 has to be greater than x. Oops. 5 plus 8 has to be greater than x. I'm going to turn this around. I like my variable to be on the left, so I know that x has to be less than 13. All right, and how about this? 8 plus x has to be greater than 5. Well, that's really kind of a nonsense statement, isn't it? Because that goes back to that original property. So this doesn't really make much sense. What this tells me is that x has to be greater than -3. But I know that x can't be negative, so I'm going to stick with this as my low end. that doesn't make any sense relative to this problem. So there's my range. X has to be greater than 3, but it has to be less than 13. So the way we would write that is as a compound inequality. X is greater than 3 and less than 13 feet. That's how we would figure that out. So guys, whenever you're trying to find the range for that third side, to get the low end, what do? You subtract the short side from the longer side, and to get the high end, you add those two. So that's really, you don't have to write the 3 inequalities every time. You just subtract to find the low end and add to find the high end. Okay, for each of the triangles below, explain why the measure of angle 1 is greater than the measure of angle 2. I'm going to pause this and fill it in. I think this is quite straightforward, so I want you to do this for your own practice and then come back and check your answers with what I have here. All right, here's how I wrote my explanations. And in the first two cases, I used the corollary to the triangle exterior angle theorem to show that the measure of angle 1 is greater than the measure of angle 2. And in, well, these random numbers 6, 7, 8, because I copied these out of the book. But in the third one, I use the comparison property of inequality to show that the measure of angle 1 is greater than the measure of angle 2. So please let me know in class if you have any troubles understanding what we've done here. Because now we're going to move on to inequalities in two triangles, and we're going to start with the Hinge theorem that says if two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, then the longer third side is opposite the larger included angle. All right, so what we got here is BA is congruent to XY. AC is congruent to XZ, but the measure of angle A is greater than the measure of angle X. Therefore, I know that BC, the length of BC, is greater than the length of XY. That's all the Hinge theorem is saying. And if you look in your book, they have an example of a door opening. This is why they call it the Hinge theorem. If you think about it, the wider the door is open, the larger the angle that is made with the door and the door frame. The more you have the door closed, the smaller that angle is. And if you made a triangle out of both of those doors, then you would have the Hinge theorem. So let's put this into practice. Write an inequality relating SK, here's SK, and YU. Here's YU. Okay, so I've got two sides that are congruent. I've got a 90-degree angle here. I got 70 degrees over here. Therefore, I know that SK is longer, right? SK is greater than YU by the Hinge theorem. Okay, how about another example? Oh, we have to draw it. An ABC. I'm going to pause while I draw this. You draw it while we're on pause, and then we'll come back and work it out. Here's what our triangles look like. Triangle ABC is right here. Triangle PQR is on the right. And I've got a set of congruent sides, well, two sets of congruent sides, and then I've got a third side that's longer. So by the Hinge theorem, I know. So really what I'm trying to do here is write an indirect proof of the Hinge theorem. So because of the Hinge theorem, I know that angle P, since it's across from, it's going to be larger, right? The measure of angle P is going to be larger than the measure of angle A. Yep, and that's what I'm trying to prove there. So what are we going to start with? We're going to assume that the measure of angle A, oops, the measure of angle A is greater than the measure of angle P, because remember in an indirect proof I just assume the opposite. Okay, so what does that tell me? That tells me, using the Hinge theorem, if angle A, the measure of, is greater than the measure of angle P, then I know that BC, has to be greater than QR, right? By the Hinge theorem. That's what the Hinge theorem tells me. If measure of angle A is greater than measure of angle P, then side BC is longer than side QR. But that is impossible because it is given that BC equals 4 and QR equals 5. So BC is not greater than QR, and measure of angle A is not greater than the measure of angle P. Therefore, I always feel like I have a lot of therefores in my paragraph proofs. Therefore, the measure of angle P has to be greater than the measure of angle A. It was really the Hinge theorem that allowed us to prove that. Okay? All right. The converse of the Hinge theorem says if two sides of one triangle are congruent to two sides of another and the third sides are not congruent, then the larger included angle is opposite the longer side. Okay, so I guess actually I think that's what we just proved. We actually just proved the converse of the Hinge theorem. So I should have put this theorem before that problem. Sorry about that. Let me go back and mark this. What I'm doing here is I'm proving the converse of the Hinge theorem. So I apologize. I should have had this after the theorem was printed, but that's what we did. And I'm not going to lie, sometimes I get my own self mixed up about which one is the theorem and which one is the converse. So I will probably forgive you for doing the same. Okay, let's look at some more examples. What is the range of possible values for the variable? Ooh, this is a good one. Okay, let's see what we got here. So we're going to use the Hinge theorem and its converse for sure. And let's see, this angle here is across from the side that's 11. 28 is across from the side that's 12. So 28's larger, right? 28 is the larger angle. So let me start with 2y minus 7. What do I know? I know that it's less than 28, right? 2y minus 7, that angle measured there is less than 28, but hey, guess what? It also has to be greater than 0. You can't leave off your left side here. So now I've got a compound inequality to solve. If you've never done it this way, it's okay. You can do it all in one line. So I'm going to add 7 to all three. So I've got 7 is less than 2y is less than 35. Now I got to divide everything by 2. Y is going to be greater than 7 halves, and it's going to be less than 35 halves. So there's the range of possible values of y. And you could plug those in Well, you know what's going to happen is that this angle here, it just has to be less than 28, and of course its measure has to be greater than 0. So let's see what we have in this scenario. This is the longer side. 15 is longer than 14, so I know that 4x minus 10 has to be less than 50, and of course it has to be greater than 0. So 10 is going to be less than 4x, and 4x is going to be less than 60. So that looks like x is going to be greater than 5 halves, and x is going to be less than 15. Unless I messed up my arithmetic, I believe that's correct. Okay, so both of those using the converse of the Hinge theorem. Okay, let's see what we got now. A quilter cuts and sews together triangles as shown in the figure. She tries to make triangle ABD and BDC equilateral, but the angle measures come out as shown. She wasn't perfect. No one is. Assume that side BD is actually the same length. Okay, so BD is the same length, congruent to itself. Which segment is the longest in the figure? Ooh, how are we going to do this? Well, we got to start with one triangle at a time. Let's start with ABD. Which is the shortest side in ABD? It's this one right here, BD, right? This is the shortest side. This would be the medium side. This would be the long side, right? So we're going to label both triangles. Okay, now I'm going to use another color. I'm going to use another color for the other triangle. Which is the longer side in BDC? Well, it's this one. BD is the longer in this one. And this is the medium, and this is the shortest side. So how are we going to figure this out? Well, look. If BD is the shortest side in the red triangle, then I know that both AB is longer than BD, and AD is certainly longer than BD. And what do I know from my triangle over here? I know that both of the sides in BDC are shorter than BD, which means that the longest side over here has to be the longest of all the sides, right? Since these two, looky here, since these two sides are shorter than BD, and both of these sides over here are longer than BD, then I know the very longest one is the longest in my left triangle. So that tells me that AD is the longest side in the figure. All right, we have a proof here. Once again, we're running a little long with this lesson, so what you're going to do here, guys, is, well, we'll do this in class tomorrow. So actually, you can give it a try if you want. I'll post the answer up here, and then we'll talk about it in class tomorrow. It's not a very difficult proof. I did it in 5 steps. So let's see what you come up with. Give it a try. Here's your solution for this proof. If you have another way that you worked it and you think it's correct and you want to talk about it in class, be delighted to do that. See you next time.